All right, welcome everyone. Today we have Samson Wang from Imperial College London, and it's my great pleasure to introduce him. So Samson has been working on error mitigation, or what are the limitations of noisy devices, and also variational quantum algorithms and quantum machine learning. And I personally worked with him when we both were at Los Alamos National Lab. So today is going to talk about, again about noisy devices, and what are the limitations of error mitigation strategies, and whether you can train variational algorithms or not. So Samson, please take it away.
Just unmute myself. Fantastic, thanks very much. Just to check again, Kunal, you can hear me through your earphones? Okay, yeah. Well, yeah, thanks very much, Kunal. Yeah, it's a pleasure and an honor to be here and be able to talk to you all today. Yeah, as Kunal mentioned, I'll talk about some work we've done on trainability of near-term algorithms.
Samson, can you make it the presentation mode? Like right now it's visible.
Is it the presentation mode? Let's see. Are you now seeing the full screen?
Right now it's black screen on my end. Yeah, now it's good.
It's the full thing? And the slides advance?
Yes.
Good, fantastic. Okay, fantastic. So everything's good. So yeah, as I said, I'll just be talking about two pieces of work we've done on the trainability of near-term algorithms. The paper codes are below. And yeah, I'm happy to keep this very loose, and so feel free to interrupt me with any questions. This is also actually the first ever in-person talk, thinking about it, that I've done for my PhD. So please bear with me if there are further technical difficulties and so on. But yeah, let's get started. So the kind of framework we'll be looking at in the talk today will be variational quantum algorithms. And for those not as familiar with the field, I'll provide like a brief introduction later on. And this talk will be split into two parts. So in the first part, we'll discuss the effect of noise on the training process of these algorithms. And then in the second part, we'll look at a class of near-term strategies called error mitigation and ask whether error mitigation can remedy these effects. So first, a brief summary of variational quantum algorithms. These are a broad class of near-term algorithms that are essentially a hybrid quantum classical algorithm. So in these algorithms, we have some quantum circuit, which is parameterized according to some strategy. Implicitly, we have to choose some structure for the parameterization, which we usually call an ansatz. We extract classical information out of the circuit through some measurement. This information is fed into a classical optimizer, which in turn updates variational parameters, and we have this kind of hybrid quantum classical optimization loop. Now, the classical optimizer essentially just sees different points on a cost function landscape in parameter space, which is simply just the expectation value of some measurement operator. And these algorithms, there's been, I guess, a big boom in research in these algorithms lately, and then they've been proposed for a huge range of problems, most famously of which probably chemistry with the variational quantum eigensolver for finding ground state energies, but also combinatorial optimization problems, finding quantities in quantum information theory and beyond. So despite this big boom in research, as with many near-term algorithms, the challenge is it's still quite unclear how performance of these algorithms scales, and theoretical results are quite sparse. One area where there have been some scaling results, however, is in the discovery of this phenomenon known as barren plateaus. So this is essentially a detrimental phenomenon that states how trainability scales as you increase the number of qubits and or increase the problem size. So these results generally look something like this. So we have the variance of the partial derivative of the cost function exponentially decaying with the number of qubits. So what this means is basically your optimization landscape is going to be, the vast majority of it is going to be exponentially flat. And because we're just having the second moment exponentially vanish, there can still be pockets of large gradient, but in general, these pockets will be exponentially hard to find. So this causes there to be a significant impairment to the trainability of these algorithms, particularly as you scale them up to larger and larger problem sizes. Yeah, we could talk about barren plateaus a lot more, and if there are more questions, I'm happy to go into more detail, but just as like a quick whirlwind tour, these were first studied in unstructured ansatzes, by which I mean for the unitary that you apply in a quantum circuit, you don't bias it towards a particular structure, so you just apply local, for instance, 1 or 2 qubit gates generally, random initialized, and keeping the 1 and 2 qubit gates generally as general as possible. So these were first found to occur when you randomly initialize such ansatzes, and this is related to the fact that the unitary you get is close to the Haar distribution. And then later these were also found to occur for global cost functions, by which I mean where you measure a global observable. So for instance, a power chop vector. Yeah, do you have a question?
Yeah, that expression you gave about the variance,
Yeah.
that would look a lot like the Fisher.
Sorry,
that would look a lot like the Fisher.
Right.
Is there some way I can think about that as like the distribution as some amount of information about the parameters in the distribution?
I think you can. I think you can, if you can think of it as and I'll maybe talk about this later on as well. There was a balance between the variance of the landscape itself and also statistical variance. And so when the statistical variance dominates over the variance of the cost landscape itself, it becomes harder and harder to extract information out of the landscape. So you have your cost landscape variance decreasing as you increase problem size, and in some sense, I think it's harder and harder to extract information given some fixed number of circuit samples. So I think that there is some connection you can make. So yes, so as I mentioned, there were originally two main ideas which seem to cause barren plateaus. Firstly, random initializing deep ansatzes, and secondly, measuring global observables. And then they were later discovered in loads of other scenarios which were related, and more that are not listed here. Moreover, barren plateau results have also been shown to be able to be generalized to so-called quantum machine learning models that employ quantum neural networks. So we could generalize our previous picture of a variational algorithm, where instead of just having a parameterized unitary U, we generalize to a channel, and also instead of just one input state, consider many input states as quantum data. But anyway, so barren plateaus so far are all looking at variational algorithms in the noise-free regime. So one question we have is, okay, variational algorithms are near-term algorithms, and noise is going to play a big factor. how does noise affect the scalability of these algorithms? Do they have further detrimental phenomena? And as I mentioned, again, like results are quite sparse, especially like theoretical results. But one area where there has been some progress is it's been found that certain algorithms display something called optimal parameter resilience, by which I mean, as you increase the noise level, the cost landscape itself might be greatly distorted, but the position of the global minimum of the cost landscape is in some sense invariant or resilient towards noise. Kunal has actually had a very nice piece of work on this himself. Now this is important because it opens a window of possibility for variational algorithms to possibly still be useful in the presence of high noise rates. So what this means is possibly if an algorithm displays optimal parameter resilience, you can still train your algorithm and extract out the optimal parameters. And then one might have two scenarios. Firstly, one might have an algorithm where you don't care too much about the exact optimized cost value itself. So if one's doing a combinatorial optimization problem, you might just want to get out a classical bit string. So finding the exact cost value isn't too important. And then the second scenario is we could, if we do care about the cost value, for instance, the cost value corresponds to an energy that we're trying to minimize. We can take the optimal parameters. We now have a recipe to prepare the optimal circuit. And then one can employ error mitigation techniques to try and approximate noise-free cost value. So given this window is open, one question we then had is, so does noise affect the training process? So if we are able to train in the presence of noise and extract these optimal parameters, then there might still be a window for variational algorithms to be useful. So to that end, we considered the following model. So here we have some layered ansatz, where we have layers of parameterized unitaries with local noise occurring before and after each gate. Unitaries we keep relatively general, and we have a product of an exponentiation of some operators HLM and some unparameterized unitary WLM. And the assumption we make is that HLM admits an efficient Pauli decomposition, by which I mean if we decompose it in the Pauli basis, we only have a polynomial number of Pauli terms. The noisy cost function is just the expectation value of some operator O. And again, we just assume that O admits an efficient Pauli decomposition. So again, only has a polynomial number of Pauli terms. The noise model we consider for a local noise model is essentially a Pauli noise model, where the quickest way to summarize it is its action on the block sphere is to compress the block sphere by non-zero amount in every direction. So for instance, this would include obviously depolarizing noise, or say bit flip plus phase flip noise, but not bit flip noise on its own. And we characterize the noise with a single parameter Q, which corresponds to the compression of the block sphere in the least squashed direction. So with this framework, we have the following result. So we find that partial derivatives of the noisy cost function are exponentially compressed as you increase the depth of your circuit. Where we have this factor in front f, where f is just polynomial to the largest eigenvalue of the operator and the measurement operator in question, and the operator appearing in the unitary. So generally, we consider f to be scaling polynomially in system size. And if this condition is satisfied, we also find that the cost function itself just exponentially concentrates to its fixed point. So the differences between different points in the cost function exponentially concentrate. What this means, of course, is that if we have linear depth or polynomial depth circuit, we have partial derivatives vanishing exponentially the problem size. under the mild assumptions I mentioned before. And so we have our cost landscape completely exponentially flattening, as in the picture on the right. This not only has implications just for designing variational algorithms, but also compilation strategies. Because, of course, we're operating in the near term, our qubits, like hardware topology, might not be all-to-all, and often could be, say, a 1D chain or a grid. So we can make some hand-wavy arguments. And of course, so again, like there aren't many results on like optimal compilation costs or the required circuit depth of variational algorithms to actually be useful. But if we make some hand-wavy arguments, certain problems when mapped to hardware topologies do have the potential to occur linear depth compilation cost or greater. For instance, if one has a 1D circuit, some recent state-of-the-art compilation results require linear depth, or in certain other problems, polynomial depth circuits, just on compiling the circuit itself. And it's also known, so for this algorithm, the QAO algorithm, is applied in something called like a number of rounds. So you apply, you're free to apply the ansatz, and this number of rounds, scaling may need to grow with N2. Similarly, for UCC ansatz, which is used for chemistry problems, again for 1D circuits with one trotter stirpits, it seems that one requires to pick up polynomial depth with state-of-the-art techniques. Just a quick word on the proof idea. So, like a main tool we use is to prove kind of entropy inequalities, so strong data processing inequalities, essentially, of the sandwich Renyi-2 entropy. So with the whole channel, which is just consisting of unitaries and the noise model we considered, we find that the resulting state quickly converges to the maximum mixed state. And this is based on some work of Hirscher et al. On entropy inequalities. Right, so I'd also just like to take a moment quickly just to really hammer home exactly why barren plateaus are a problem. So one response or one question we often get is, why can't you just, for instance, okay, your cost function landscape is flattened, why can't you just stretch it out? And this also ties into the question asked earlier. So the key thing is, again, is to remember we're in the near-term regime, and shots or circuit samples are like a resource that we don't want to spend too much of, or don't have too much access to. So we need to think about shots on a near-term device. So we can consider the following problem, which can be considered to be like a simple primitive of what an optimizer would actually want to do. So the task is, given this dark blue dot and this light blue dot, can I distinguish whether the dark blue dot is above or below the light blue dot in cost value? But we have to remember, like, if we are actually going to implement a variational quantum algorithm, we'd have to do an experiment. And so these cost values on this cost landscape we've been talking about actually, of course, just correspond to mean values of some probability distribution that we have to sample from in our experiment. So what this means is that if we have a barren plateau or noise-induced barren plateau, when the landscape is compressed and these two probability distributions are exponentially close to each other, it becomes exponentially hard to distinguish between these 2 points. And this, of course, and barren plateau results are generally expressed in terms of gradients or partial derivatives, but this argument also applies to gradient-free optimizers. So you could consider, for instance, simplex-based methods where these 2 points don't necessarily need to be close to each other, they could be far apart. But again, you would still need to extract information out of the cost landscape, distinguish whether one point is higher or lower than another. And so similar arguments apply. So the main takeaway is that these noise-induced effects affect the trainability of these algorithms by exponentially degrading the resolvability of the landscape. And so they thus require the classical optimizer to spend an exponential number of shots or circuit samples. And this is explicitly why they are a problem. So to summarize this part of the talk, yeah, we have these noise-induced effects where under certain noise models, if the circuit depth scales linearly or worse in the number of qubits, we have trainability exponentially degrading. And this occurs irrespective of this wide literature that has come about in avoiding noise-free bound plateaus. So methods that can prevent noise-free bound plateaus that have been studied don't seem to help with these noise-induced so-called bound plateaus. And in terms of how to avoid, of course, one can look for ways to reduce circuit depth or smarter compilation strategies or algorithms. And of course, we also can always reduce the noise level on our hardware. But another kind of immediate question is, can we apply error mitigation techniques to resolve this kind of problem? So this brings us on to the second part of the talk: can error mitigation remove the exponential scaling of these noise-induced effects? So just to briefly summarize what error mitigation is, these are a new broad class of near-term strategies to mitigate the effects of noise on expectation values. So the main idea is, okay, ideally we'd like to prepare these noise-free cost values, but we only have access to noisy cost values where we might have state preparation and measurement errors or gate errors. So a broad class of techniques has been studied recently to say, okay, given we can only prepare noisy cost values of this form, can we come up with some nice tricks to, for instance, run multiple circuits or run different circuits to approximate the noise-free cost value? And this has been, work has been done in error mitigation, both for gate errors and measurement errors alike. So one example, a prominent example originally proposed by the IBM group is that of zero noise extrapolation. So the idea here is we're going to run our circuit of interest, but we're going to run multiple copies of it. And so given the ability to artificially, in some way, augment the noise level in the circuit, we're going to run this circuit at varying levels of noise and augment the noise level. And given information from these many different circuit runs, expectation values at different levels of noise, apply some extrapolation technique to essentially extrapolate back to a noise, an approximation at least of a noise-free expectation value. Another recent technique that's been proposed concurrently by the Google group and a group in Oxford is that of virtual distillation. So here the idea is we're going to prepare our final state of interest multiple times and prepare it in a kind of tensor product. Then by applying a kind of permutation operator, we're going to prepare essentially the quantity below. So O is our desired measurement operator. And so we will prepare capital M copies of our state of interest and extract out the following mitigated cost value. The idea being that if our intended final state is pure and the noise doesn't distort the dominant eigenvalue of this state, then this will essentially approximate the noise-free cost value as we increase M. Okay. So there are many other error mitigation techniques, and we tried to encapsulate all of them into a kind of general framework. So now we're saying, given some rho, given some unitary we want to apply U, and given some measurement operator O, we can in general apply some different input state sigma in, apply some different circuit corresponding to some unitary channel V, and apply some general measurement operator on the tensor product system X. And additionally, we can also have access to some ancillary qubits. So we write our general mitigated cost value as follows. So this encapsulates, so this is essentially the sum of expectation values, where the expectation values are just some expectation of some measurement operator X on the tensor product space. And this includes the previous two strategies discussed, so zero noise extrapolation and virtual distillation, and also includes other prominent methods in the literature, so for instance, quasi-probability methods and Clifford data regression. So with this kind of unified framework of error mitigation, we prove the following result. So we show that there exists some parameter independent quantity f such that the error mitigated cost value exponentially concentrates on f as you increase the problem size, if again we have linear depth circuits. So if our circuits that we're applying B of theta are linear depth. So this essentially states that this exponential cost concentrating effect cannot be avoided with error mitigation without spending an exponential number of resources. So the first way to see this is if A max, T, and M max are polynomials. So here, A max we see on the right is the coefficient we apply when we classically post-process expectation values. T is just the number of terms in this linear combination, so how many different circuits are we going to run? And M max is, out of all of these expectation values, what's the largest number of state copies we prefer. So one situation is A max, T, and M max are all only polynomially increasing in N, in which case we have our usual Baron-Courtot result. Another scenario is if A max or T are exponentially large, then we might not have an exponentially decaying right-hand side. But in this case, so if A max is exponentially large, then you're artificially multiplying all your expectation values by some coefficient A, which is exponentially large. So this is going to exponentially blow up your statistical variance in expectation values. And so again, you're going to have to spend an exponential number of shots. Likewise, again, if M max is exponentially large, we use an exponential number of state copies. This isn't good either. So far we've dealt with the asymptotic regime, but one could still ask, okay, some people might view kind of exponential effects due to noise as simply delaying the timeline on an engineering timescale. Yep, hello.
So when like recently I saw like a few months ago a result by and others. I mean, what is the difference between that? I think they had like, if you have equalizing noise, then in presence of that, you will need exponential many samples for integration. So what is the difference? Like, what is it?
Oh, this is the result of Ruji. Right. When they did the noise analysis, I think basically their result is exactly the same to us. So like our works came out concurrently. They used our NIBP, our noise-induced Baron-Courtot model of noise. So their work was looking, as you know, at like looking at the circuit sampling costs.
They were also like, this generalized model, mitigation, Oxford mitigation.
Right. yeah, so they were looking at sampling costs and then using the noise-induced parameter noise model, they came to basically the same conclusion. Yeah.
But were they using different tools? Like was he using resource theory framework to arrive to his results?
Yeah, that tools to, so that paper was also just generally looking at circuit sample cost. So yeah, those tools were different to the ones we used. So they treated it a bit more formally actually. So like they looked at error mitigation as like one classical channel, and then they use kind of tools from information theory to look at sampling cost. Yeah, so the final bit I just wanted to talk about is so okay, this was asymptotics. Some people might argue, okay, like they're just asymptotic results, so it might just delay like the engineering timeline for variational algorithms to be useful, if they could be useful. For instance, if we just lower the noise rates enough, maybe we can squeeze something out. In which case, we might still want to actually just mitigate these effects with error mitigation, even if we can't remove exponential scaling of resources. So does error mitigation help, and which ones do help? So to this end, we study quantities of this form, which essentially quantifies the change in resolvability of your landscape after applying error mitigation. So this is the ratio. Sorry?
Does this like I mean this requirement of exponentially on the sample statement, does this also apply to probabilistic error cancellation?
It does, yeah. So for instance, in probabilistic error cancellation, I mean you're not going to be trying a tensor product of states, but you're essentially just adding in extra gates. So this is equivalent to just modifying your.
Recently, there was some result by IBM group. They learned the noise model, and after that, they were saying that they were getting improvement, but they were saying that maybe their noise model was. Yeah, I think they had some not so bad.
Right. I should also stress, like error mitigation, it seems like, and there's been so many results from error mitigation, it does seem to be very useful actually in correcting expectation values. So in many cases, you can actually get close to your noise-free expectation value. But this is a bit different. This is saying, this is looking at training. So it's saying if we have these noise-induced effects where your training decays exponentially, then error mitigation isn't going to help you kind of navigate your cost aspect. That said, if you just wanted to prepare a circuit and not do any training, yes, it seems like error mitigation is very useful, and we're not really making any statement about that. Yeah. That is, unless like well, we would still make a statement that you would have to spend you would have to spend more shots. But I think from like an application point of view, probably this isn't too relevant. I think they would be happy to spend the extra shots if they're just preparing one circuit.
And I think maybe they are doing small scale experiments. So
yeah.
if you count
right
to do that number of qubits, maybe it's still fine. But yeah, but I don't know what happens to the variance arguments even for those experiments.
The variance arguments?
Yeah, like if they must be calculating some cost value, even if it's not variational at the end of the day.
Yeah. So you would still have to spend more shots, and I think it's I mean it is widely also known. Error mitigation itself, like implicitly requires more shots in itself.
Yeah.
But it seems like even like with what we have right now, I don't know the exact system sizes they're looking at, they are still able to get satisfactory results. That's why I guess error mitigation has been so popular. That it does seem to be useful. So yes, so coming back to this, so we're asking whether error mitigation can help in the non-asymptotic regime. So we're considering the relative resolvability quantities, which is the ratio of the number of shots we need to distinguish 2 points on the cost landscape in the noisy setting versus distinguishing those 2 points in the error mitigated setting. So you can write this as the product of 2 terms, where the first term, Cm, is the mitigated cost value, and C tilde is the noisy cost value. So this term on the right is simply just the increase in separation of cost values after we've error mitigated. So this first term on the right, we expect to generally increase as we error mitigate if we have these concentrating effects of noise. We would hope, for instance, that error mitigated cost landscape would more closely correspond to the noise-free cost landscape. So yes, of course, we would expect this quantity on the right to be greater than 1, basically. And on the left-hand side, we have this gamma term, which is the increase in statistical variance after error mitigation. And now this, as I just mentioned, is generally thought to actually increase, and sometimes in some protocols increase quite a lot. So now we see there's a trade-off. So we have these two effects. On the right-hand side, we have this quantity which we'd expect to increase with error mitigation, and on the left-hand side, we'd expect the statistical variance to increase. So 1 over gamma would be smaller than 1 generally. So we have these 2 competing effects, and we can see this visually here. So here, like the 2 points on the cost landscape, yes, they're more separated, but now the variance when we actually want to do experiments and extract information out of these 2 points, it's unclear whether it's easier or harder to extract information if you want to distinguish 2 points. And actually, so we find that in many cases, error mitigation protocols adversely affect the resolvability of the landscape. So they actually make things worse overall. So kind of baby example is we can look at global depolarizing noise and virtual distillation protocol. So noise of the form like a global depolarizing noise model, we find that this chi quantity for every pair of points on the cost landscape is quickly decreasing in M, which is the number of state copies we prepare, and this is always less than or equal to 1. This means actually, like ironically, like the more state copies you try and use, the worse resolvability gets. Right, and we have more general results. For instance, one of them here, we have noise using zero noise extrapolation, utilizing Richardson extrapolation, which is just a kind of known extrapolation technique under a relatively general noise. If we now consider a kind of averaged chi, where instead of just looking at the cost difference between 2 points on the landscape, we average over the whole landscape, over all pairs of costs. Over all pairs of cost function differences. Then under the assumption that the distortion of the landscape isn't too high, where we assume the global cost minimum isn't just is still on average lower than most of the other points, we have again some kind of inequality for this average chi, which I've missed out a bit here, but this is always also less than or equal to 1. And we have similar results obtained for virtual distillation and zero noise extrapolation. When doing different kinds of averaging, also averaging over a class of noisy states with the same purity, and we find that the resolvability gets worse as your purity decreases. So if your noise is taking away the purity of your output states, then the resolvability after applying error mitigation gets worse and worse. There's some intuition from the paper you mentioned, so from Ruiji's paper. One can think of, in some circumstances, of the data processing inequality. For example, if one's just doing some simple post-processing of one circuit, then yeah, data processing inequality automatically tells you that you can't increase resolvability. But of course, there are some error mitigation protocols that also fall outside of this kind of framework. And lastly, just some numerics. So we are able to find certain protocols that are able to show some improvement in trainability. The main one we look at is fitted data regression. So this is where we prepare training states, which are noisy states, and run some kind of learning process to try and learn an affine map that maps the noisy cost values to noise-free cost values. And so in these database approaches, we do find there is some improvement here. So here we have CDR, data regression, outperforming just noisy optimization for different numbers of system sizes. And again, we have a few theoretical results in virtual distillation. So here we just have some example of looking at an implementation of virtual distillation, and we see it gets significantly worse results after optimizing. And here on the bottom, we have n tot, which is the total number of shots used. So even if we give virtual distillation more circuit samples, an order of magnitude more circuit samples, it seems it can't perform well as just basic noisy optimization. So to summarize the main points, so we found that noise can exponentially degrade the trainability of variational algorithms by making cost landscapes exponentially hard to resolve. We also find error mitigation or broad class of error mitigation techniques cannot avoid the scaling issue without spending at least an exponential number of resources. And finally, we find many scenarios where error mitigation can worsen the trainability, but there is some scope perhaps for some protocols to improve trainability, possibly in database mitigation techniques. So with that, I'd like to conclude and just say thanks for listening, and I'd be happy to take any questions.
Hi. So first of all, one thing I wasn't 100% clear on. So these results that you've got, they're taking into account both the noiseless parameters on them and the noisy parameters at the same time, or things get even worse with the
things would get even worse. So the results are independent of whether or not you have a noise-free band plateau.
Okay.
So noise-free band plateaus tend to occur due to, for instance, the structure of the ansatz you're applying. So if you had an ansatz with such a structure and this kind of noise model, you would essentially get both effects. But the results are independent of those noise-free results.
Okay.
Yeah, I wonder if there are any cases that noise actually helps, like symmetry breaking between locality and
well, it's interesting. Yeah, there has been some results on this. Exactly on symmetry breaking. So, like, the interesting thing is certain parameterized circuits of the form we're looking at appear to have like degenerate minima, and noise, it seems, can break the symmetry of these degenerate minima. But this actually then impairs the training process often, because it means you used to have like lots of global minima, but now a lot of those global minima are now local minima. So you end up getting stuck in local minima. So it's actually the kind of opposite. Yeah.
And the class function that you use here, so the result is for any kind of class function, or for example, it depends on the class function is local or global. How does the noise affect?
Yeah, so the locality of the observable you're measuring doesn't play a part. So the only term that comes up is the infinity norm of the observable. So as long as this is bounded, the results apply. And also, so we were looking at linear. We were looking at linear cost functions, but also, oh, sorry, I stopped sharing screen. maybe it would be too much effort to get it back, but there was, we also have this result that we can generalize linear cost functions to non-linear cost functions that people might use traditionally in machine learning, so logarithmic cost functions, and generic bandpater results that apply to linear cost functions also apply to these more exotic non-linear cost functions.
Yeah, is there any intuition for why this Clifford data regression was somehow working? I actually didn't know about that.
Yeah, yeah, I can talk more about that. So that's just the reference. So Clifford data regression, the strategy is let's define like an affine map from a noisy cost function to the noise free. And so if you just go through the like calculation, you find that like in terms of changing the resolvability in the way that we looked at it, this has a neutral effect on the result. So it doesn't, chi is basically equal to 1. The reason is because you're just scaling by some coefficient. So your points are separated by some factor, let's say a, but your statistical variance also is stretched by some factor a. So these two effects basically balance each other out. But of course, like Clifford data regression is like quite a general, it seems to be useful in quite generic scenarios. So there are other effects due to noise on the cost function landscape. So for instance, in propagating local minima. So if Clifford data regression is able to solve any other defects due to noise, then it has a hope of like improving the training process. So purely looking at like resolvability, it has a neutral effect, but this opens the opportunities for if it solves any other problems due to noise, you see an improvement in trainability, which I think intuitively, like we generally expect, it would help somehow.
I see. But then are results numerical, or this argument is
results are numerical? I mean, we can show Clifford data regression has neutral effect on resolvability, so that's quite simple to show. Yeah, that's about it. Yeah.
And then is that method scalable? I mean, in the sense that they train on a Clifford circuit.
Yes.
And which is fine, but then if I want to like generalize it to arbitrary circuit on 200 qubits, like what's the consensus on that?
As far as I'm aware, the scalability is unclear. So you have a few things to consider. For instance, they have to, it's called Clifford data regression, but you actually have to inject a few non-Clifford circuits, as you know, and the amount of non-Clifford circuits you need to use in your training process to get good results is unclear. And then also, you see, you're now training lots and lots of circuits, so the total shot cost is quite hard to accommodate for. And I don't think it's generally known how to scale it as well.
I see. Yeah. If there are any questions from the Zoom audience, please unmute yourself and ask. Otherwise, yeah, let's thank Samson again. And Samson is around QuiCS all day, so feel free to reach out to him.
Thanks very much.